Good morning, Year 11. Today we're going to look at the energy stored in a spring when it's either stretched or compressed. If you haven't had a chance to do the do now yet, please do so. Pause the video and then see what you got. So question 1, the unit we should use for mass. Hopefully we all got kilograms. Let's see if I can get my pen up. So this should have been kilograms. What should we use for speed? That was meters per second. The equation for kinetic energy. So EK is a half mv squared. You might have seen it as EK is 0.5 mv squared. Either of those is fine. How much kinetic energy would a 2 kilogram car travelling at 4 meters per second have? So the kinetic energy is going to be 0.5 or a half times its mass times 4 squared. So that would come out as 16 joules. What happens to kinetic energy when speed is doubled? It increases by a factor of 4 because it's squared. Increases by a factor of 4 because there's a square relationship there. Okay, so here's our direct instruction. So we're going to look at what springs are and what we mean when we talk about something called the spring constant. So if you can imagine these two springs, this first spring is going to be really, really hard to stretch. Look how thick it is. That's a really stiff spring, whereas this one is really, really weak. It would be really, really easy to stretch. So this one is easy to stretch. This would have a low spring constant, whereas this one over here, this would be really hard to stretch. So this one has a high spring constant. So easy to stretch gives you a low spring constant, hard to stretch gives you a high spring constant. So if you imagine if we stretch these both by the same length, this one would take a lot more force to stretch, so this one would be storing a lot more energy. We can calculate that energy stored with the equation I'm about to show you. So your elastic potential energy, we mentioned this yesterday, or the day before yesterday, sorry. So we have our elastic potential energy, and that is equal to 0.5 or a half, I'll use a half today, times the spring constant, times by the extension squared. So it kind of looks really, really similar to that kinetic energy equation we saw yesterday. So this says extension, it's not very neat, sorry. So extension is just the change in length. If you can imagine, if a spring starts off at 10 centimeters and when you stretch it, it goes to 12, it's changed by 2 centimeters, so that extension will be 2 centimeters. We'll have a look at some units. Well, elastic potential energy, it's an energy, so that's going to be joules, capital J. The spring constant is newtons per meter, and the extension is in meters. So if you have centimeters, for example, you'd have to divide that by 100 to turn it into meters, so just like we saw yesterday. Alright, let's have a look at a specific example. So This spring here has a spring constant K. This is given the symbol K, this is given the symbol E, and this is given the symbol capital E with a little e next to it. So the K, the spring constant, is 4 newtons per metre. That means if I applied a force of 4 newtons to this spring, it would stretch by 1 metre. We'll have a look at how much it stretches by as well. So it started off here at 6 centimetres and it stretched all the way to down here at 8.3 centimetres. So we've got 8.3 minus 6 gives me 2.3 centimetres. That should say 2.3, it's not very clear. 2.3 centimetres. But just like we mentioned earlier, this centimetres is a problem. I need to divide this by 100 to get my distance in metres. So my extension is actually going to be 0.023 metres. So we'll do our calculation up here. So our elastic potential energy, EE, is store 0.5. So again, I'm using the half or the 0.5 interchangeably. So 0.5 times K, the spring constant, that's the measure of how stiff the spring is, times by the extension squared. Substituting our values, and again we must lay it out like this all the time. It just makes our lives so much easier and the examiners know exactly what they're looking for. So the spring constant was 4 and the extension was 0.023, and do not forget that squared, it's really easy to do. I'm going to type that into my calculator. 0.5 times 4 times 0.023 squared. The calculator says 1.058 times 10 to the negative 3. So I'm going to write that in a more familiar way. That's 0.001, and it would round to 1. And the unit, of course, is joules, as we mentioned earlier. Okay, so let's have a go at some of these. I'm going to model probably one of the hardest things you'll come across, and it says a spring constant has, or spring has a constant of 16 newtons per metre. It has 8 joules stored in it, but we don't know how far it's extended. So that's what it's asking us to work out. So I'm going to have to work out what the E is. So I need to rearrange our equation to make E the subject. So 0.5 times mass. Ooh. That is another common mistake. Please don't do that. Don't get confused between mass and spring constant. One's for calculating kinetic energy, one's for calculating energy stored by the spring. That should be a K times E squared. We need to make sure we've got E on its own, so we'll bring these two underneath, which will give me the energy stored by the spring divided by 0.5 times K, which will give me E squared. My problem here is I don't want this squared by the E, I want the E to be on its own. So to get rid of a squared, I have to square root both sides. So I'll square root that, I'll square root that, and happily a square root cancels a square. So I'll get my rubber out. Hopefully I should be able to get rid of that, and we're good to go. So we're going to be using this equation that we've just rearranged. So I will write my equation first every time, even though it's written over here. I'm going to write it again. So energy stored over 0.5 times K. We'll substitute in. So the energy stored was 8 joules. That's divided by 0.5 times the spring constant, which was 16. And that's all square rooted. I'll type that into my calculator. I've got a feeling it's going to come out as 1, but we'll see. So 8 over 0.5 times 16, all square rooted, is indeed 1. So that's quite nice. So the extension is 1 meter. So you guys have to do exactly the same with some of these questions down here. So some of them are more straightforward than others. I'm going to write 1 or 2 equations that you might need here. So force is K times extension. So I think if you've got this equation, and this equation, you should be able to answer all of them. Our next activity is using graphs to figure out how much energy we've got stored. So calculate how much energy is stored by the springs shown on the graph below when it is stretched for 0.6 meters. That's what you're going to have to do. You guys need to do it for 0.4. The one we're going to do together is a 0.4, not 0.6. So when I'm doing this, I will go to 0.4. I'll draw a line up until I hit here, and that tells me what my extension is. If we have a force extension graphs, the area under the graph equals energy stored. So all I have to do here is extension times force divided by 2. So my energy stored is going to be a half F, the force, times by extension. So this is a combination of these two equations. So we can use this one, substitute it into that one, and it gives us this equation here. But we've just deduced it from the graph. So let's put some numbers into this one. So a half times 100 is the force, times by 0.4, and we'll use our calculator, and that comes out as, oops, it's not very clear, that comes out as 20 joules. 20 joules. So you need to do exactly what we did here, but you're using 0.6 rather than 0.4.